I'm the founder of Real Research. I'm also a product manager and researcher at the Mass General Hospital and the Broad Institute. That's how it works in the academic area. And the meetup organizer. My previous background is at the software high-tech industry and entrepreneurship. In the last few years, I shifted my career path to the biology and bioinformatics fields. I worked as a technician, actually doing wet lab at the Whitehead Institute. And then I work on the analysis side at the Broad. I'm here today to discuss the challenges of machine learning for better care, healthcare, very related to what Gaurav said about. And these are the things that I'm currently working on at our Real Research venture. So the part that I know by heart is this. So I'll talk a little bit about the motivation to use machine learning at the healthcare industry, and based on that, on the goals. For the people that are not foundation medicine people, what is precision medicine? The data challenges that we have, Gaurav touched it this a little bit. Why machine learning? And few models that are, or the workflow models that currently being considered, potential solutions for these challenges, and what is our real research. So on one side, what we have right now is technology that is able to kill cells, sick cells, selectively. For people familiar a little bit with this field, edit genes at the body, like CRISPR for people from foundation, and selectively inhibiting protein in the body for cells that are sick based on mutation or different markers that we can see. And the big thing about that, it's not about each one of these drugs. It's about this being extendable, that once we know what the target is, then we can use these technologies to kill other or to treat other diseases. On the other hand, we have the healthcare industry that suffers from diagnostic errors. Many times I would find people, cancer is it's more using genomics more frequently, but this is basically not about cancer. We can repurpose it for every disease that has features that can be used. And in rare diseases, there are also in cancer, there are many cases when we don't have precise diagnosis for the patient. We still don't know what is the best target for the patient from different reasons, and we have a limited data-driven medical decision. So we do have people sharing the data, building protocols based on data, but it's very limited. Clinical trials are very small. We're trying now to go to a larger clinical trials, but we are not there yet. So the question that we are asking, how can we merge technology, amazing technology that we currently have, with healthcare challenges and for the patient benefit, of course. And based on that, our goals will be to improve care across diseases. And better care, we mean data-driven diagnostics, data-driven therapy matching, and drug development. So all these features that we find basically is potential targets. So precision medicine, for people who are not familiar with precision medicine, we see here a melanoma patient. It's a very famous picture in the medical field. We see here a patient with melanoma, many lesions on his body. In his body, melanoma is a skin cancer, and he was lucky to have a BRAF mutation. BRAF is a gene on the genome, specific location with specific area, coding areas, but it doesn't really matter. A selective marker that we can hit when we treat this patient. And luckily, this patient was sensitive to this drug, to the BRAF inhibitor, because having this specific V600E mutation doesn't mean that you're going to respond for that. And after a few weeks of treatment, he looks like this, the picture on the right side, with no lesions in his body. And this is quite amazing without using any chemotherapy and with relatively a patient that's feeling relatively well. However, this is not relevant for all melanoma patients. This specific patient developed resistance to this therapy, so it was not the end of the story for him. And repurposed this drug for other cancers. For example, colon cancer is not straightforward. And we ask ourselves, how can we extend this temporary success for other treatments? And the answer is in the data. That's where machine learning comes to play. In some ways, in a very simplified way, we want to start from D1 diagnostic and get into a cure, another destination. We want to know what are the paths, what are the treatments that we want, or what are the stations that we need to go on the way. So what are the data challenges? And I'll give you one example of data in this field. It's very, very dramatically different from the industry, for someone who came from the industry. So the goal is to let the data tell the story. And then we have many feature categories. Omics is a family of many, many categories: DNA, RNA, proteomics, epigenomics, metabolism. I'll show you a few of them. Tons of features. Clinical data. For DNA, for example, 2% of the DNA is 20,000 gene coding areas, and another 98% is things that we want to use for machine learning, and each one of them has endless variation. Not endless, but millions of values. We have many values. We have different types of data. Sometimes it's continuous, sometimes it's discrete, sometimes it's sparse, sometimes it's anything that you can think. Clinical could be a text that you need to categorize. Hospitals that are generating very limited data. Most of the data is missing. We have conflict between assays that are done in different hospitals, even for the same patient. We have wide variety of techniques. Now everybody's talking about single cell. It's about taking one cell and sequencing its DNA or RNA. In the past, we used to do it, or still doing it very, for most of the places, as a bulk. You take a piece of the tumor or tissue or a disease and you sequence it. There is no data formatting standard, nothing at all. Everybody's generating his data in a different standard. And we don't know what is a normal, because the cell, based on its purpose, different activity, different expression, different usage of the gene. And of course, therapy, if someone was taking drug X, Y, and Z, and the other one was taking Y, X, and Z, does it mean that it is the same therapy? How we define that? And then we get even a larger matrix of options and paths. Another challenge that we have at this field is that not everybody is generating data that is can be used for machine learning, like genomics or other omics. Patient privacy protection is a huge challenge. Even the data that we have to go into HIPAA and IRB, many institutes that are trying to save the patient and provide science tools to work, but this is a very contradicting. And we have the academic credit barriers. A lot of the people need to publish. This is the academic rewarding system, and for that, they keep the data close to themselves, and it's hard to share the data. Example of data in this foundation medicine example, no privacy protection issue. And so that's the kind of report that foundation medicine is providing. There is more to it, but basically it's the names of the genes and mutations that they are harboring. On the other side, 23andMe with some kind of clinical information. We don't need to understand exactly what is happening inside, but it's not the same format. It's not that we can push it to the same training model and find easily. There's a lot of pre-processing work to be done here. So why machine learning? So the cell processes are very complex and convoluted. TMAP is peanuts for the cell. Cell is very convoluted. There are many connections being done there, many regulations maybe that are affecting each other. And if we let the basic biology people try to find out all these cell processes and their relations, it's going to be a long time, years, maybe decades, maybe more. So we're trying to get insight from machine learning with a little understanding of, or less understanding of what is happening in the cell. and maximize this information for the patient care. One insight is able to change many people's lives, because once you find one feature that can help us, then there are many people that you can treat it that way. So one model workflow that I'm currently working on, but I'm not showing, I'm going to show results next time that I'm going to present because it's too early, is a diagnostic prediction model. So basically saying who is sick, who is healthy. You can also derive some markers and target candidates based on that. So I'm trying, if someone can stop me if I'm not simplifying enough. So we have the patient with all this data, with all these features that are super long list, and the clinical information. And we want to know if he's sick or not only cancer. So this is a little bit about the feature. We have the DNA that is the genomic feature, the RNA for transcriptome, but it really doesn't matter. It's just each one of them is a science by itself. And then we have the training data matrix that is the molecular and clinical information, the patient, and then we want to predict if it's sick or healthy. If you notice, there is no notion of disease here. We, in my view, and I think some people will agree with me, we don't know the labels of disease or all diseases right now. And we can say that if someone was diagnosed with one disease, maybe a breast cancer might be a subset of a breast cancer. If it's a colorectal cancer, it can be a subset. But it's not only cancer, other diseases also. So if I don't know the right labels, I cannot train the data based on these labels. So going from training data for sick and healthy was making sense more here. And I'll talk about therapy, and then you will see maybe more sense into it. And what can we use it for? For diagnostic tests based on blood or buccal smear or others that we know if someone is sick or not. It is being used right now, such diagnostic tests, but not with such features or machine learning based on that for response for therapy or for biopsies, but this is one of them. We can identify known and unknown genetic diseases because based on this feature, we can categorize new categories of disease, use it for prenatal tests, disease predisposition, and preventative medicine. And then there is the therapy matching prediction model that could also yield us with markers, target candidates, and therapy matching. So for that, there are two options here. One of them is per therapy. Look at the patient data and give type of response. If it's a cure, if it's a stable disease, I want to know what is the probability to get to each one of them per therapy. The other one was using all therapies, and then the label is a set of the therapy and the response. Like therapy one could be the one drug, and then the response could be for cure, or this drug for a stable disease, and then it's T1, R2. In both models here, the therapy definition by itself is challenging. Sometimes, and most of the data right now that we have on genomics is the cancer, and in cancer there is a lot about the patient and a lot of evaluation before giving treatment, changing treatments. It's not straightforward. And there is no disease notion, because we believe that if therapy is responding best for a specific set of features, minimal set of features, then we don't need to categorize the disease by that. We need to personalize also the identification of the disease. Okay, so the training model will look something like that, and the deliveries will be a specific therapy evaluation, drug development targets, things that I already said. And for the second one, is going to be best therapy assignment. For the doctor, it's going to look something like that. Maybe it makes more sense. Is this patient, what therapy info is available, and what is the probability for that to work with his specific feature information. Same kind of implications. The one thing that we couldn't achieve, and the other one was drug repurposing for known and newly identified diseases. So if we see this is first time, we don't know what to do with that, Maybe it shares some common features with other diseases, and we can use it in a more straightforward way. Of course, there is FDA, there's a lot of regulation behind it, but this is a shorter way than having someone to agree to investigate this specific disease. Okay, potential solution for all these challenges with the data and with the specific area is use machine learning. What can you lose? Collaboration with pharma companies, hospitals, DNA-based diagnostic facilities like Foundation Medicine. There is a huge hype around IoT, Internet of Things, like Fitbit and others that are taking a lot of information, following people in treatment, and using their personal smartphones. Data scientists, machine learners, bioinformatics, biologists, all of them need to gather together because there is a lot of sense of also knowing what is the drug and what are the features that are being used. Real research by itself is a crowdsourcing project for identifying all these labels, challenges, who is sick, why, and what therapy will work best for him. It works on the Google Cloud platform, uses TensorFlow. Anyone is welcome to contribute. Initial results are going to be available and be shared soon. Something that I want to push on this meetup is if someone wants to work on a small group, brainstorming, challenging. Machine learning is new to many people, and there are new challenges coming in. And that's my thank you. I think I made the time if anyone has questions. And Shana Tova for anyone who is here.